So just 2 minutes. Just 2 minutes and we'll start. Yes, sir.
Okay.
Yeah.
So we are.
I'm audible, na?
Yes, sir. Yes, sir.
Okay.
So we are moving ahead for today's session. And X-ray instrumentation. He has published several research papers of national and international review. He has been actively involved in various projects and missions of Indian Space Research Organization. So I request you, sir, to please let us know more about AstroSat. Please, sir.
Hello. I will start my talk.
Yes, sir.
So, I will, hi, good afternoon everybody. I am Vivek Agrawal from Space Astronomy Group, URSC Bangalore. And I will speak on AstroSat view of neutron star low mass X-ray binaries. As you know that, basically I will speak on X-ray domain of these sources, neutron star sources, which is found in low mass X-ray binaries. So, hello. So, I will speak on AstroSat view of neutron star low mass X-ray binaries. So, as you know that all the optical observations are done from the ground-based observatory, like we have Hanle Observatory, we have Nainital Observatory, we have own telescope at Pandit Ravi Shankar University. You might have done some observation from optical telescope. Okay, so all the optical observation is done from the ground-based observatory, and also radio observation also is done from the ground-based observatories. So, but carry out the extra observation, we need to go to the space. Why? This is because our atmosphere is opaque to the X-ray radiation. Like here I am showing the one plot which shows that at what height different kind of radiation can penetrate. So here is showing the altitude, here is showing the wavelength of the radiation. So X-ray cannot penetrate below 40 kilometers and height, and atmosphere doesn't allow X-ray to go below the 40 kilometer height. So we have to send some satellite observatory or some balloon kind of observation above the 40 kilometer to observe the X-ray radiation. So X-ray observation is basically the X-ray, gamma ray, and UV observations are done basically from the space-based observatory or balloon experiments. So to carry out such study, in early times, rocket experiment was sent which carries the X-ray counters, and they discovered that in something like 1960, around 1960, 1950 and 1949, they discovered that sun is powerful source of the X-rays, and they thought that why not explore the X-ray sky in detail. So first powerful extrasolar X-ray source in the direction of constellation Scorpius X was discovered by rocket experiment on 18 June 1962. This source was named SQX1. Discovery of this source opened a new window in the X-ray astronomy. Subsequently, many satellite-based observations were conducted, and many satellites was sent like Uhuru, Chandra, XOM, Deposec. So many satellites like our AstroSat was sent to study these cosmic X-ray sources in very great detail, and what is their properties, what is how X-ray is produced in these stars, what is the procedure to investigate all those things phenomena, to search for the new X-ray sources and new processes. Many satellite-based observation and balloon-based observations are sent from the to the sky. Sorry. Thus, astronomers felt that there should be many more sources which are stronger emitter of the high energy radiation like X-ray, gamma ray, and UV radiation. And first X-ray observatory, Uru, was launched from on 12 December 1972 to study these sources in great detail, to find their properties and to discover many more X-ray sources. So first Uru observations revealed that there is one more X-ray source called Centaurus X3. Centaurus means is in Centaurus constellation, and X3 means X-ray, and third object in this near this constellation. So strong modulation of 4.84 seconds were observed. This was termed as X-ray pulsation. So X-ray pulsation of 4.84 seconds were observed from this source, and they also found that pulsation varied slightly with time, periodically with 2.09 days. So this graph shows that pulse arrival time. So what happens is, these pulses are produced by the neutron star, which is spinning. The spinning neutron start producing the X-ray pulses, and when they rotate around the orbit, this pulse arrival time changes with as go away and come forward toward us. So this is the where they found that this neutron star are rotating around the one companion with period of 2.09 days. So it was recognized that Centaurus X3 is a binary system in which neutron star accretes matter from normal companion. Neutron star in this system is rotating about 2.09 days around the messy normal companion. So, and Uru found many more X-ray sources in the X-ray sky. Around 339 sources were cataloged from this source. Sources were found from this Uru observations. So these are the missions which were sent to explore the X-ray sky. First mission was sent Uhuru, which worked from 72 to 73 and carried proportional counters and worked at 20 kV. So similar to that, many more satellites were sent. The important satellites are like XMM, Chandra. Chandra carries X-ray telescope, basically X-ray optics they carry, and XM also carries X-ray optics. Spatial resolution of the Chandra observatory is around 0.5 arc-second, and initial mission like Uhuru has spatial resolution of 2 to 1 degree. So there was significant improvement in spatial resolution and effective area. And XM sent two optical X-ray optics. So X-ray resolution is 6 arc-second. So like that, spatial resolution, effective area, and other things improve by day. So that improve the sensitivity and X-ray. We can explore the X-ray scan in more great detail. So what is the X-ray binary? So I told that many more sources were found that they are found in a binary system. Binary system means one object like a neutron star or black hole is orbiting around the normal companion star, So these are called X-ray binaries. These are the gravitationally bound system of two stars, where one object is neutron star black hole, and another star is normal star like sun, or could be more messy object also. And compact objects pulls matter from the normal companion. So there is a picture of X-ray binaries. This is the at the center here one compact object like neutron star black hole are sitting, and then these are accreting material from the companion star. This is companion star like normal star, and matter is transformed from the companion stars to the compact objects, and this material lose the angular momentum and form an accretion disk around this compact object. Okay, and when they spiral, they lose their angular momentum. Also, potential energy is converted into kinetic energy, which is converted into thermal energy, and that energy released in the form of the X-ray radiation. Because plasma in this of the gas is very hot, is 10⁻⁷ Kelvin. So in this temperature, X-ray radiation is emitted. So this is one component of accretion flow is your accretion disk, and this source also show jets of outflow. Kind of, this is called jet, and also corona is there. Corona is a hot thermal non-thermal plasma around the accretion disk, and it can also generate the disk wind. So there are several components of the accretion flow are there. So you have a company star, your compact object, your accretion disk, your jets, your winds, your accretion streams. So many variety of, and this star is rotating around the compact object. So you see several other phenomena like eclipses. You see the different kind of pulsation. You see some this neutron star is rotating, and if it is axis is spin axis is misaligned with the magnetic axis, and suppose accretion is channeled to the pole, it will generate the X-ray pulses like we see in the center of X-ray. So what is source of energy in the sources? The accretion is the source of energy in the X-ray binary. So suppose mass of the company is m and accretion rate is m dot. So energy released, potential energy released is around gmm dot by r. M dot is your accretion rate. So this much energy per unit time will be released. That could be equated to eta m dot c square. So eta is the efficiency of accretion. Efficiency of accretion is around 10% per neutron star of 10 km radius. But nuclear fusion has only the efficiency of 0.007 or less than 1%. So accretion is more powerful source of energy compared to the nuclear fusion. Nuclear fusion is working in the star like sun and many other places where nuclear fusion converting the hydrogen fuel to helium, and then it is giving some sort of energy, releasing energy. So we found that accretion is more powerful compared to the nuclear fusion and generates the most of the power in the X-ray binary system. Then there is a what is the different types of radiative process I will speak out. There are so process by which radiation is emitted could be very different for different kind of environment. So black body radiation is basically emitted from the neutron star surface, and surface which is in thermal equilibrium. So black body emission, you know the emission which is emitted from the thermal radiation from the neutron star surface. There is another kind of emission which is called power law. This is non-thermal radiation because it is emitted from the non-thermal population of the electrons. And this is better example is synchrotron radiation. Synchrotron is your non-thermal emission. And hot plasma of gas emits thermal bremsstrahlung radiation. So this bremsstrahlung emission is emitted when why is the bremsstrahlung when particle is accelerated in the field of nucleus, they will emit some radiation. So that radiation is called thermal bremsstrahlung emission. Then another kind of emission is thermal compression. What is compression means? You understand what is compression scattering. Compression scattering, one electron, photon scatter with the electron and lose or gain some energy in this process of scattering. When this gains energy, it is called the inverse compression scattering. When and inverse compression scattering has power law, is slightly cut off. That is the thermal compression model. Why thermal compression? Because it is emitted from the thermal population of electrons. Non-thermal radiation emitted from the non-thermal population of electrons. And thermal population means which follows the Maxwellian distribution. Then it comes to the multicolor display body emission. Multicolor display emission is emitted from accretion disk. We can divide accretion into several parts. Each part here, like is shown the green, red. Each part of we can divide the accretion disk in several parts. Each part is in thermal equilibrium. So each part will emit the black body radiation. And when you and temperature increases as we move inside. So each part will emit different kind thermal radiation with different temperature. So when you sum this black body radiation, and we'll get the integrated spectrum called multicolor display body emission. So there is a different kind of emission mechanism which is working in the X-ray binaries in the X-ray disk. The thermal compression is produced in the corona basically, and thermal flame strong is more common in the hot gases like cluster of galaxy or somewhere. Power law emission or synchrotron emission is produced generally in the jets where the accelerated electrons are there in shock waves, and then black body radiation is emitted from the thermal radiation emitted from the surface of the neutron star. So this is different kind of radiation versus in the X-ray binary working on. Now what is neutron star? So neutron stars are in the state of stellar evolution. You know that when supernova explosion happens, core is left. That core is made of total neutron, some fraction of protons, and some iron nuclei. So this star is supported by degeneracy pressure of the neutron. So this star is called neutron stars. And radius of neutron star varies from 10 to 20 kilometers. Mass is around 1.4 to 2 solar mass. And core density is nuclear density. So what is means suppose you have 1 teaspoon of the neutron star matter, and that weight of this matter will be more than the whole population of the Earth. That is the density of the neutron star. And magnetic field is very, very high. Magnetic field is 7 Gauss to 10 or 15 Gauss. What is Earth's magnetic field is few Gauss. So there is enormous density, magnetic field, and enormous gravity is there. So that is the very next neutron star, very exotic. So we use the data from AstroSat mission to study these stars, neutron stars in X-ray binaries. So AstroSat has many instruments, five instruments. One is called large area X-ray proportional counter. Why is proportional counter? Because it has wires, it has gas field, argon gas and xenon gas field inside, and this is the gas which is used to detect the X-rays from the sky. And there is a soft X-ray telescope which uses the X-ray optics. Then you have UAT which has UV mirrors, it's optical telescope, and another is your SSM, scanning sky monitor, which has a position sensitive wire, gas based detectors, and coated mask. When this SSM rotates in own axis, and that is this observation used to locate the X-ray transients in the sky, and alert is generated. Based on that, all the instruments can be pointed towards the new transients discovered. So this is the whole. And UAT works in UV range, LAX PC works in 2 to 80 kV extra energy range, and CGT works in 20 to 200 kV energy range, and SXT works in 0.5 to 10 kV energy range. So this is the different kind of instrument is there in the astrosat. And this is the right side shows the effective area of the lax PC counter. So you can see that RXT PCA, which is also carries a proportional counter, proportional counter, and astrosat also carries a proportional counter. But effective area of the astrosat lax PC is more compared to the RXT PCA, because gas pressure, one of the thing, gas pressure is more, and so it can be the more effective area in the higher energy area. Now I am talking about X-ray binaries. So X-ray binaries can be classified into two types of X-ray binaries. One is low mass X-ray binaries, which has companion star less than 1 solar mass. Company star is less than 1 solar mass, and HSB, where company star is greater than 12 solar mass. So this is X-ray binary. Low mass X-ray means company is less massive. High mass X-ray means company is more massive. And also more massive is this is new type star, OB type star. And low mass X-ray and lead type star. Then again neutron star low mass X-ray binaries are further divided into two types of X-ray binaries. One is G source, which this is the color card diagram. Color card diagram means when you divide the whole light spectrum in 4 energy bands and take the ratio of count rate in the lower energy band, that's the soft color. Ratio of count rate in higher energy band is the hard color. If you plot, Z track is traced in the G sources, and R sources show the ethyl type track. G sources these are persistent sources. Luminosity is very high. Is the brightest source in the X-ray sky. Brightest X-ray binaries. Ethyl sources have luminosity in this range 0.01 to 0.2 LED. So, property I will speak on jet and ethyl sources. Jet and ethyl sources show thermonuclear burst. So this shows typical thermonuclear burst from the ethyl source. Rise time is generally 0.5 to 5 seconds. Decay time is exponential, 10 to 100 seconds. Energy rate 39 action. What is thermonuclear burst? This is activated material on the surface of neutron star burn unstably. There is a helium fusion, hydrogen fusion they keep on going on in the surface of neutron star. When fusion is uncontrolled and unstable, then you see the thermonuclear flash. This source is also quasi-periodic oscillation. What is quasi-periodic oscillation? It's not perfectly periodic. When you take Fourier transform of the light curve, you see the two peaks in the power spectrum. This is 200 kilohertz QPO seen in the one of the source SQX1. So there are different kind of property these sources show. So HQ means I forgot to put this. In G sources, this branch is called horizontal branch. This is called flaring branch. This is called the this normal branch. This is called the flaring branch. So upper left is called horizontal branch. Middle one is called normal branch. And right one is called the flaring branch. Why flaring branch? Because they show flare in this branch. This is called a flaring branch. So different kind of QPO are associated with the different kinds, portion of the light curve. Different portion of the branches. So there is called a horizontal branch oscillation. Horizontal branch oscillations are seen in the horizontal branch. So this is the frequency of this oscillation ranges from 20 to 100 Hz. Then similar to there is a normal flaring oscillation, which frequency ranges from 5 to 20 Hz. And this is called twin kilohertz QPO. This is oscillation frequency. This is 200 to 1200 Hz. So this shows the QPO seen in the SQX1. So this is the twin kilohertz QPO seen from the SQX1. So this is in the Fourier domain, not in the ground domain. This is Fourier domain it is seen. If you take the Fourier transform of the light curve, you see two peaks in the one peak like 20 to 100 hertz or something in the power spectrum. So this is called the Q quasi-periodic oscillation. Suppose you take the Fourier transform of the sinusoidal variation, you get single peak, not get broad peak. But when these oscillations are closely packed and amplitude is varying, so if you take Fourier transform, that you will get the broad peak instead of one narrow peak delta function. This is called QPO. And spectrum, what is spectrum? Spectrum is nothing but spectrum is you will plot intensity of photons versus energy. That plot is called a spectrum. The spectrum of G source is soft and shows cut off at 6 kV. It also says spectrum is so two kind of states, hard and soft state. Soft state spectrum it also is similar to G sources. So it also says and G sources has similar spectrum in soft state. It also says hard spectrum is different. Hard state is generally coincide with the island branch. This has two branches. One is this is called in metal sources. This is called island banana branch. This is called the island branch. In color diagram, I explained that what is color diagram. Ratio counter in two high energy band is called hard color. A ratio counter in two lower energy band is called the soft color. So this when it plotted against each other, we get the different kind of structure in the color diagram. That's called so this is banana branch and this is the island branch. So island branch spectrum is generally hard and so banana state spectrum generally soft. So soft state spectrum is very similar to G sources. So this is the properties of timing properties and spectral properties of G and G data sources. So motivation behind interpreting these sources, what is the mass acceleration process? Whether mass acceleration is changing, what is changing? One thing is what is changing along this jet. Why these sources so beautiful tracks, different kind of tracks, different all the six. So there are six sources. All the sources show jet diagram. Why these sources so beautiful this kind of pattern? So what is changing here? Whether mass acceleration is changing along this track, increasing, decreasing, what is happening? So that is one of the investigation. That is one of the motivation behind it. What is accretion flow geometry? What is the origin behind the entire track? Then these sources show type fast extravert. Basically, at all sources, not G sources show extravert. Some of the G sources show extravert, one or two, but mostly at all sources show the type fast extravert. Type fast extravert I told thermonuclear crisis. So, what is the effect of thermonuclear burst on the emission process and associated changes in accretion geometry? How accretion geometry changes when extravert occurs? Second thing is, I saw that there is also this source also show the non-thermal emission. So what is the mechanism which produces the non-thermal emission? So these are the basic questions you should ask. And what is the mechanism behind the quasi-periodic oscillation? So this is the motivation behind studying these sources. So studying these sources, we took 4 examples, 2 ATA sources and 2 G sources. These sources were observed by Astro Observatory for different times and different exposure time. So 4 is 1704, I minus 44 is ATA source. Later 1705 means it's quad minus 44 is quadrant, RA and DEC. So this is R and DEC, 1826 minus 230, R and DEC. And this is the so this is LMC galaxy, large magnetic storm. This is the second source in large magnetic storm. This is the first extra galactic G source, and only one G source which is extra galactic.
कहीं पे डाल दिया ताकि मैं आपको या मेरे नंबर है.
So the source 4U1705 minus 44 is type first extraversal and classified as an ATA source.
हाँ उसमें फोन कर लेना जब आप
And this is the light curve of this source. Light curve means we plot time versus count rate versus time. Count rate in 3 to 60 kV band plotted against the time. So these sources show very high activity. So these sources were there in the high soft state. Soft means soft spectral states. and high states. So, and the source stretched a banana track in the color card diagram. This is called a banana track. So we divided this track in the different different portions, different sections, 6-7 sections, and they studied what spectral parameter, what timing parameter is changing across this track. So we can pinpoint what is changing along the track. That will tell that why this track is produced. So I already explained that what is thermal compression model. Is an inverse compression model and produced by thermal population of electron. Thermal population of electron means Maxwellian distribution. So this electron is produced by this is called thermal compression. Thermal compression is produced by corona. There is corona around the accretion disk. That when emission from seed photons, from accretion disk are neutron surface scattered through this corona. Inverse compression cutting will happen. Photon will get energy, electron will lose energy. So that thermal compression model. So
इसका आवाज बहुत अच्छा क्रिस्टल क्लियर है सर का आवाज थोड़ा सा वहाँ पे घूम रहा था पर ये अभी एकदम अच्छा चल
variable power is called non-thermal radiation.
और दूसरा क्या भी
This model is suitable to
अभी हमने क्या खिड़की पूरा खुलवा दी है इसलिए जो रिफ्लेक्ट
black species spectrum of the position of the the hard tail observed is source is variable. So the hard tail is not showing
चलो ना
very
उसका क्या करना है उसको बाद में बता देना मेरे को
कौन सा
एक आध बार वो फ्लैश प्लेयर का बताना
फ्लैश के नहीं आजकल वो क्या है दूसरी टेक्नोलॉजी यूज कर रहे हैं मेरे को चेक करना पड़ेगा क्या टेक्नोलॉजी
पता
है
है वही बच्चे ने very dense कहां से लाया मैडम बोलने वाली सब
pull करो this temperature is only 2.5 to 3 K. Generally hard corona there will be temperature up to 50 to 100 K.
नहीं है खोजना पर मैं भिजवा दूंगा
corona is
खोज के
cool
हाँ
and it has temperature of 2.5 to 3 K. The right side I show the variation of the spectral parameter
नहीं अभी वो
along the banana tree.
बता दो जो कैसे कैसे
So
इसमें
most noticeable changes were
मैं जिसको दी
was seen in the optical depth. Optical depth means density of plasma. Density of plasma increases along the banana tree. So second thing is we also find that temperature of plasma decreases along the banana tree. So two things here, temperature of plasma changes increasing and optical depth is increasing. So there could be that we propose that there could be that accretion disk is there and some material is radiation pressure is driving some material into the corona. So if you drive some material to corona will become more dense. So density of corona and optical depth will increase. And if you are more dense, with more number of scattering. More number of scattering means the electron will lose some energy, more rapidly lose energy. So its instant temperature will come down. So these two things are found in the this interesting thing of found. So that kind of changes is driving the along the banana tree. Second thing we found that Y parameter. What is Y parameter? Is energy gain. Energy gain per scattering after any scattering. So the energy gain is increasing along the banana tree. So this is an interesting thing we observe in this source. Second source, this is D source. This is D source. And this is a persistent neutron star low mass. I explained what is low mass system, what is neutron star, and what is G source. This is classified as G source. Doing explosion observation, we achieved complete jet profile. So you can see the jet type diagram was seen during the astration observation. This jet diagram is seen during the astration observation. This is the flaring branch. I explained that during this source show the flare. The flare is corresponds to this flaring branch. So during the flaring branch, this source shows the flare, X-ray flares. So X-ray flares are observed from this source, and flaring branch are also observed from the source. And second thing is, Second thing is we also observe different branches like heart branch and nerve branch. So all the three branches with flaring branch, with flare observed from this source during the few hours of the 1 or 2 day observation of this source. So this is the uniqueness of the laxity. The spectra at, again I explain what is spectrum. Spectrum at different parts of G track can be modeled with thermal compression model. Again explain what is thermal compression model and power law plus iron law. And corona is again here also you found a G source. G source as we expected, corona should be after the thick.
खाना मिला जी?
हाँ हाँ जी
We
सर।
observe
नहीं,
this
इसको
property
पूछा।
from this
अच्छा
source.
इसको पूछा ये कहाँ से आ गया?
Non-thermal component
आनंद वो उसको बता दी वो
इसको
was
रंगोली
weak
का भी।
in the
2-3 में तो हम बहुत कंफ्यूज हुए क्योंकि एक जैसे मतलब लेवल पे थे पर अच्छे
बाद में मेरे को 13 और 18 भी अच्छे लगे।
इसीलिए मैं बोली कि हमको मतलब ऐसा नहीं है कि
2 के कंपैरिजन में ना
So you
13
propose
और
that
8
this
जो
OJT
थोड़े
is
ज़्यादा
hybrid
अच्छे
thermal
लगे।
non-thermal.
असल में
Hybrid
13
means
बनाया
hybrid
जो
corona means
कॉन्सेप्ट वाइज पर उसमें
thermal
फिनिशिंग भी तो
thermal
करना
thermal
पड़ता है
electrons
कलर
and
वाला
non-thermal electrons.
हाँ
कलर
कॉन्सेप्ट बहुत अच्छे अच्छे
हाँ,
हैं वो जैसे वो ये वाला नहीं है वही इसरो वाली जो बात जो तू 13 नंबर को बोल रहा है
Thermal
ना
electrons
कॉन्सेप्ट वाइज वो
compression
बहुत अच्छा है लेकिन वो
non-thermal
फिनिशिंग फिर अब कैसे
additional
करोगे
or electrons.
रंगोली में तो दोनों देखना पड़ता है
That in the 3 to 60 kV band, but about 20 kV flux was very less, so we decided to feed in the 0.5 to 20 kV spectrum of joint spectrum of SST, soft X-ray telescope, large area X-ray proportional counter, and with pure computation model, inverse counter scattering model. Then I explain what is inverse counter scattering. So we found that in low energy band disk is absent. That is a very good observation. So either disk may be very far from the complete object, or it is covered from the corona. And covered from corona, so we cannot see the accretion disk. The two possibilities we proposed. Again, compression in pool and after the team. We divided the track into different parts and studied the spectral evolution. So this is the KT is decreasing. From HB to FB it decreases, and optical depth is almost constant in FB is increasing. So there is general pattern in threading branch, always optical depth is increasing, and optical depth is either decreasing or remain constant in the NB and HB. So that is we observe that there is clear pattern on that. So that suggests that there is a feedback between corona and accretion disk that is governing the how with change in accretion rate maybe governing the its movement on the Jade and Natal track. That is our conclusion. Then also we studied the broadband spectral property of clocked buster. Clock buster means these sources give regular X-ray burst, thermonuclear flash. This source GS 1.26-238 is regular X-ray burst. This is X-ray buster. So that's why it's called clocked X-ray burst. Regular every 1 hour, 2 hour, 3 hours it will show the X-ray burst. So this source was discovered by Ginga satellite. This is one of the Japanese satellite, and then astral observation was observed in soft state. So this is the maxi light curve, top panel is, and bottom panel is your back light curve. Maxi means this is the monitor of all sky X-ray imaging, which is sky surveyor, X-ray sky surveyor in the International Space Station. And this is the BATS instrument, burst alert telescope, which is there in SIP satellite. So this light curve in the 20 to 100 kV. This is the light curve in the 2 to 20 kV band. So it is very clear that 2 to 20 kV light, 2 to 20 kV count was very less. Means source and 20 to 100 kV the count rate was high. The source was in the hard spectral state in starting, and then source may transition to soft spectral states. So in the soft spectral states, we observe the source from the astroset. So astroset observe the source in soft spectral state, not in the hard spectral state. So this is the light curve. This is the two occasions observed. One is green and pink, magenta curve shows that astroset observation. Two occasions. So this is the light curve in two different energy band: 3 to 60 kV energy band, 3 to 60 kV energy band, 6 to 20 kV energy band. This is the light curve for observation B, magenta one. You can see that there is light curve is variable. It is varying, not too much varying, but it is varying. And this second one is showed that light count rate is decreasing with time. So we observe variability in the light curve doing this observation. Then we detected two thermonuclear bursts from this source. Two thermonuclear bursts. So this is thermonuclear burst in 3 to 60 kV, 3 to 20 kV, and 20 to 60 kV. This observation we also saw different energy band thermonuclear burst. So as you can see that in 20 to 60 kV, there is thermonuclear burst is observed till 20 to 60 kV, both the cases. So what is the earlier observation? Earlier observation is that basically from the RST satellite. So previous observation from the RST satellite. RST satellites found that in high energy band, actually X-ray burst is not observed. X-ray burst, there is count rate is decreased, not increased. So this is the unusual types of triphasic X-ray burst. So generally RSTA observed triphasic X-ray burst, thermonuclear burst in the hard spectroscopy, not in the soft spectroscopy. We observe the X-ray burst in the soft spectroscopy. So that is the difference in the our observation. Because this source observed soft spectroscopy and this so type first observed in soft state different from the type first X-ray burst or thermonuclear burst observed in the hard state. So that is the what is the basic what is the why it is different. I will just tell you. So so then we also studied the we also made a color diagram. Color diagram is ratio of again I told ratio of count rate in 2 high energy band is called hard color. Ratio of 2 low energy band is called the ratio of count rate in 2 lower energy band are called the soft color. So created the this color diagram and it is the kind of track called banana track, almost very similar to the fragmented diagrams. And then we model the this source required a reflection model also. Reflection means you have X-ray from corona which is reflected from the accretion disk. This is the reflection model. Then we have in case come with thermal compression model, multicolor disk model. I explained what is multicolor disk model. Just know, multicolor disk model is you divide the different parts. Each part producing the X-ray emission, and you sum it is called the multicolor disk emission. So we observe the multicolor disk emission, thermal compression model, and reflection. And the optical depth we found that increased and compared corona becomes cooler. So this is the standard. So it's all the sample of sources show that along the FB with a change in mass accretion rate, increase in mass accretion rate, optical depth always increases and compared corona becomes cooler. Either in FB or in the banana track, in the high accretion rate state. That is the general observation we found. We also found that strong reflection in the high intensity state. That could be the fact that in the high intensity state, disk can extend very close to component object, so you see more reflection from the corona. If your corona is not changing much. Then we study the relation of burst emission. So this is the spectrum of the burst. The burst has more count, more photons, and persistent emission, which is emission during the non-burst emission has a low power, low count rate, low photon intensity. Okay, so this is the and also we found that photon index is flatter. Photon is flatter because of the repeated counter scattering. Repeated counter scattering will increase the energy of the photons, so it becomes flatter. So our photon index will decrease. It will put more photon in the high energy band. So that is the why we are getting more. We are getting emission up to 20 to 60 kV. That explains the why you see the hard X-rays in the sources. The hard X-rays we found na. Hard X-rays why you see because of repeated counter scattering. And cooling is less efficient compared to the heating or compared to the compressed of scattering. Cooling is there, but cooling is less significant. So that's why 20 to 60 kV count really is increased compared to the when you have during the RC time source on hard state means corona may be more hotter and cooling may be more efficient. So that cooling may cost 20 to 60 kV count. But in our case source was soft state, the cooling was less efficient, but there was the index becomes flatter because repeated counter scattering. So we see the excess in 20 to 60 kg range. That was our observations. And we also found that accretion-based component disappeared. So why accretion-based component disappeared? Here accretion-based component is not there, but in burst means why it is not there? Because burst will produce large amount of X-ray flux, So radiation pressure will be very, very high. That radiation pressure will push the disc outside. So that way disc will move away. I will not see this accretion disc in this source, in the peak of the X-ray burst. So that was our observation. How much time I have? I am finished now. So, our conclusion is there is a how jet track is produced. So jet track is produced because of the feedback between corona and accretion disk. Corona accretion means there is a cooling, heating, flow of matter inside, outside happening. That kind of feedback is producing the movement of jet track with change in the accretion rate. So that was the one of the reasons which explains the jet track or étal track in the G étal sources. Non-thermal component, I explained that non-thermal component is produced by the hybrid thermal and non-thermal propulsion electron. So there are two other models, is the relativistic inflow, that's the bulk model compression, and jet base of the jet. So both model is not working because during the FP radiation pressure will be very high, so it will suppress the bulk flow, and also during the FP you don't see the radio emission, means there is no non-thermal propulsion electron in the base of the radio jet, so you don't expect any non-thermal component cannot come from the base of the jet. So that is the one of the reasons. So we provide that hybrid thermal non-thermal propulsion electron. I explained what is thermal propulsion electron, what is non-thermal propulsion electron. Non-thermal means which following power law. Thermal means which has Maxwellian distribution. So these two population of electrons is there in the same place. That is this called hybrid thermal and non-thermal population. Not this radiation is not produced from the DMC or radio base of the radiation. Then there is this source is also the thermonuclear X-ray burst. So we found two thermonuclear X-ray burst and found that this burst pushes the accretion disk away, so it modifies the accretion geometry. Also, optical depth is also increased with the burst. Means it throws the material to the corona. So there is a first X-ray burst affects their surrounding jet around the source. So environment around the source. So either by pushing material or pushing the accretion away, so it changes the geometry, it changes the emission mechanism, and that is the conclusion from the thermonuclear burst. So thank you for your attention. I have finished here. Any question you can ask me.
Thank you so much, sir. Anyone who want to ask any question? Quick questions. Hello, sir. Hello, sir. Hello. Hello. Hello, sir.
Hi, Chakradhari. Are you there?
Yes, sir. Yes, sir. So there is no such questions from the PPT, but students wanted to ask that if they want to do research project under you or in ISRO, how they can do. All the students are from astronomy, like they have their specialization in astronomy. They're pursuing that. So if they want to do research project under you, how they can do.
Why is it very simple? I can.
Hello, sir.
Hi, Chakradhari. Are you there?
Yes, sir. So there is no such questions from the PPT, but students wanted to ask that if they want to do research project
आवाज आ रही है सर?
आवाज आ रही है, आवाज आ रही है।
Have this specialization
Sir, students wanted to ask you this, if they wanted to do research project under you, what is the procedure and how will it do?
What I could not get your voice, what you mean by research project?
So am I audible now?
Audible now, audible now.
So students wanted to ask you that if they want to do research project under you, so how, or under ISRO or anywhere, how they can do it, and what are the procedures?
आवाज आ रही है सर?
आवाज आ रही है। Application करना होगा from STAR project, STAR project, and if you want to there are junior research fellowship. If time to time every year they do junior research fellowship, you can
Am
apply
I
for that
audible
and
now?
join the audible now. Exactly.
So students wanted to ask you that if they want to do research
Guide
project
some
under you,
guide
so
the
how,
small
or
student
under
to
ISRO or
doing the
anywhere, how
research
they can
work.
do it,
Through that
what
you
are
can
the
do that
procedures?
research work with you.
Okay, sir. Thank you so much. Thank you so much, sir, for joining.
Thank you, thank you.
Thank you.